And our first speaker is Diego Riste, and we'll open the afternoon session. Thanks.
Thank you. Yes, this works great. Thank you, Maria, and thank you, everybody, for giving me the opportunity to speak here today. It's exciting when finally an experimentalist has a chance to meet with theorists. It hasn't happened often enough. I'm Diego Riste, and I come from Raytheon BBN Technologies, which is located in Cambridge, Massachusetts. And this title is quite generic, as you can see. And the reason is that I'm putting together basically two different ideas, two different topics. One is an experiment we did demonstrating some advantage using a quantum circuit over basically the equivalent on using classical learning. And the second part is about hardware we've been developing that might be helpful in implementations of quantum machine learning protocols. Before I start, a quick overview of our group. This is a smaller group of BBN Technologies, which is part of Raytheon. This is basically our cryogenic, let's say, lab, part of which works on quantum engineering and computing, and the bold names are those who were involved in these experiments. As I said, I'm an experimentalist, and the first part of the talk, I will, there is one slide missing, okay, never mind. The first part of the talk, I will introduce the experiment we did a couple of years ago using 5 superconducting qubits, which basically shows that we can implement a particular problem, the so-called learning parity with noise. You might be familiar with it. It's a classical old problem. And we implement it on a quantum hardware, and we demonstrate that quantum learning can be done faster than classical learning. And in the second part, as I mentioned, I will show some demonstrations of the hardware that we are developing to control qubits and measure them that has been developed in the context of error correction or in order to manipulate logical qubits, but that I think might be relevant also for in this context. So let's start with part 1. It's going to be a shorter one. Basically, I will point again to a subset of problems that we heard about in some way already today that rely on an oracle to figure out basically if the solution is correct or basically on probing the oracle a certain number of times to determine, for example, what the label is for this specific oracle. One problem basically relies on querying the oracle multiple times, and then the efficiency or the computational complexity of the problem is linked to the number of times that you need to query the oracle. So the particular problem that we're investigating here is learning parity with noise. And we basically implemented with 5 transmons. And we show that at least 100 times advantage, as I explained in what sense this occurs, in manipulating the data in a quantum way compared to classically. And this is an experiment that was proposed at IBM a couple of years earlier, and that we implemented together with IBM at BBN. So let's start with the classical version of the problem. What we have is basically an oracle that implements some function that is a subset of all possible functions. In this case, it's a parity function over a subset of input bits. You have n data bits and one ancilla that is used to store the result of this parity measurement or this parity function. And the goal of this problem is to figure out which oracle is encoded in this function here. So the difference is basically how many bits are marked to compute the parity. So the result of this parity is going to be in this bit over here. And if nothing happens, these bits are going to match the input data bits. And the way to do this classically would be just to call this oracle many times with no access to the input, but we have some random input state. And if you probe this oracle enough times, you will be able, in a perfect world, just by Gaussian elimination or just having enough statistics to figure out what this function is. So just to give you an example, a very simple oracle which has only 2 data bits and 1 ancilla with random inputs. So for instance, you want to determine what this k is over here. You start pushing a button, and every time you click, you'll get a different result, so a different output. So for example, if you get 0, 0 for the data bits, then you measure that the ancilla is in 0. Obviously, that's not enough. You keep going, and you get, for example, for 0 and 1, you get a 1. And if you have enough statistics, you'll figure out eventually that the parity that you are computing over here is the parity of both data qubits. So whenever they match, you get the result 0. When they're different, you get the result 1. So far, very easy. One can just do this enough times and determine what the K is. However, if there are errors either in the oracle or in the readout these bits, then things get harder because it's harder to correlate these results with the ancilla. So you need many more probing of this system. Why can't I go back? Here it is. In order to figure out with some probability, with some confidence, what the K is. Now, how to make this quantum? Basically, we start by trying to get the same statistics, converting this problem into a quantum processor. We basically construct a parity function by using a series of CNOT gates with the same target, the ancilla here, and there is a CNOT gate per 1 in this parity function. And at the end, we measure all these bits, and we try to get an estimate of what this K should be. Now, the device we are using for this is a 5-qubit device provided by IBM, which is basically very similar to the one that is available, the first example in the IBM quantum experience. This experiment was done a little earlier than that became available. And the difference here what's important between the classical and quantum protocol is that what we do with the data bits at the end, with the result of this parity function. So classically, the only thing you could do is to measure all the bits here, and so you get some, again, like earlier, you get some combinations of zeros and ones, and you just keep repeating this. If you have a quantum processor like here, you're also able to do some coherent operations, in this case, Hadamard gates on all the output bits or qubits, and in which case you basically can convert this state into one that is gives you the solution with much higher probability. And I will show you how in a second. So for example, let's start with the classical case. It's still a quantum oracle, as you can see, but it's classical in the sense that we only read out the final state with no processing. We have an example here of different queries. For each one, we get some parity result over here, and sometimes this result could be wrong because of noise either in the gates or in the readout of the qubits. Nevertheless, you can find the most consistent solution with all these queries, which in this case is the correct solution 1-1. And if you can compare the number of queries required for certain error probability, you see that this decreases, of course, as you increase the number of queries. And the problem is harder when there are a larger number of excitations. That's because you need to apply more 2-qubit gates in this protocol. Now, if you go on the quantum case, the difference is, as I mentioned, that you apply Hadamard gates at the end. And ideally, the output will become the following, where the solution is going to become entangled with ancilla in state 1. Which means that ideally every time you project the qubit and the ancilla in the excited state, then the desired solution is going to be in the data qubit. So you can just read them. If you can read them perfectly, you get the solution. So for example, you do the same kind of statistics and discard all the cases where the result of the ancilla is 0, or you only keep those which have 1. Sorry, this should be discarded, not this one. So you're keeping only these 3. And then you do a majority vote on the data qubit results so that you can get the result basically, which is again 1-1. And this is basically the probability of error that you get as a function of number of queries. Again, and you can compare the two cases in the classical processing and the quantum processing, and you can see that the number of queries to reach 1% probability becomes much smaller for the quantum case than for classical. This is for a register of 2 data qubits. Now we can also go to a larger register, as large as the processor allows us. So first we do with 3 data qubits. And this is the comparison with the classical case that takes a long time or a larger number of queries to even approach the 1% error. Whereas in a quantum case, this seems almost unaffected by, well, at least in this small range, unaffected by the size, or very, very small difference. Now we can also apply a smarter processing of the results, do some Bayesian inference on the classical data to improve on the learning procedure, which definitely improves for the classical case, but doing also a similar kind of processing that uses the analog voltage results helps also the quantum case, so the gap is preserved in some way. So another interesting thing is that we can add additional noise to this process to see how actually the 2 classical quantum cases perform. And So one thing we could do is to increase the readout error probability. For instance, for the ancilla, that should contain the, in the classical case, it has a result. In the quantum case, it will have the, it's the condition for post-selecting. And we can increase the error starting from the minimum that is basically around 5% due to the readout infidelity of the ancilla qubit. We can increase it artificially, and you can see that in this case, the number of queries required increases dramatically for the classical case, and it's not such a significant increase in the quantum case instead. The main reason is that even if you discard output the data, in the quantum case, you still have the result, the solution in the other half. So even if you don't know anything about the ancilla, you get a good chance to get the solution with a small number of queries. Similarly, we can also increase the readout error on the data qubits. Now the problem becomes harder for both quantum and classical case, but there is always a gap, a significant gap between the two. And so far I've shown you what basically we were able to do a couple of years ago with the hardware that we had available. Now, if you go on even in the IBM Quantum Experience page, you can find the larger qubit systems, and indeed, another group in Italy has demonstrated the same experiment using 16 qubits, also proving a gap between classical and quantum processing. So the main point of all of this was to show what we were able to do basically with small devices and limited functionalities. The rest of the talk, I want to introduce some additional capabilities that we have in controlling the qubits that we have demonstrated also on a subset on a small devices. And an example of digital feedback. So what do I mean by digital feedback? It's basically the act of controlling qubits depending on projective measurements of one or more of them. And there are several applications for this that go from simple fast qubit reset to measurement-based gates, majority vote or real-time error correction for encoded qubits. And what maybe connects more to the topic of this week is also for adaptive protocols, of which these two are only recent examples. And there are more, as we heard this morning, of course. And a lot of demonstrations have been done already on feedback control with qubits, especially superconducting qubits. But here I want to show a little more of what's possible by processing these measurement results in real time. So in this talk, I'll mainly focus on some implementations of this type of feedback and leave the rest, hopefully, for future experiments. So the simplest case we'll go to discuss is the fast feedback reset, qubit reset. But first, I just want to give you an idea of how our experimental system works. Basically, what our control relies on is this custom-made hardware that has been developed at BBN in the last 5 years or so, which consists of a trigger distribution module that basically controls several IPS, the so-called IPS, which are arbitrary pulse sequencers. Each of them has 2 channels that are used either for control or readout of 1 or more qubits. And now all these pulses are being sent to the device that is in the dilution refrigerator. And everything that comes back is demodulated and acquired by a digitizer. And the interesting part is that this loop is closed in the sense that the result of these measurements are fed back to the trigger distribution model that could either broadcast them back to the control units or do some additional processing before doing that so that the sequence can depend on actual result of the measurements in real time. As I mentioned, the simplest example of this is qubit reset, where the goal is simply to initialize the qubits in a ground state as fast as we can. Instead of waiting for qubit relaxation, that is usually one has to wait a number at least 3 or 5 times the relaxation time. In this case, one could do a measurement, and then if the qubit is measured in 1, you would do a corrective pi pulse to prepare the ground state. Otherwise, you just leave it the way it is. And using this architecture, basically, we demonstrate simple things like doing a reset simultaneously of 3 qubits. And what you see on the right here is the probability of preparing the ground state for different initial states basically using the 8 computational states of the 3 qubits. You will see here quite a broad range of fidelities or probabilities for different qubits. The main reason here is that the different readout fidelities that we had available at that time. One has a Josephson parametric amplifier that improves the readout fidelity. The other ones didn't have. But the point here is that we can basically digitize the signal independently for the 3 readout channels and basically target the ground state for each of them. A different example, which is also relatively simple, is to create a deterministic entanglement by measurement and feedback, or in this case, it's feed-forward. The reason is that we basically do a parity measurement as in the, basically as in the surface code, but only using 3 qubits here, where you map the parity of the 2 data qubits into the ancilla, and then you can do measurements of the ancilla to determine what the parity is. And depending on the parity, you can post-select the tomography on the data qubits. And in one case, if you start from a superposition, you will get an even Bell state, ideally. And in the other case, you will get the odd Bell state. Now, this is all done by post-selection. What you would like to do is to obtain this entanglement deterministically. And in order to do that, you will have to apply a pi pulse conditionally on the measurement result, so that if, for example, you want to target the odd parity state, whenever you get the even entangled state, you would just apply a pi pulse with the correct phase in order to restore the odd state. So what you see here, the state tomography that is unconditioned, so basically by averaging over all the possible results, you will still obtain a Bell state with such fidelity deterministically. So these are still measurements and there are still all results that rely on a single measurement result to do one gate, conditional on that. There are different cases so you can explore. For instance, the measurement-based T-gate. Obviously, the one I'm showing you now is a T-gate on physical qubits, which is very simple. But the idea is that even when you will have logical qubits, you won't be able to apply, at least for some codes, you won't be able to apply the T-gate transversally, which means you have to find a different way to do that. So one way to do this is to use an ancillary qubit to basically entangle your qubit with, and then perform a measurement on the ancilla, and depending on the result, you would either have applied the T-gate or the same gate apart from a correction, which is an inverse S here. So we basically, just to demonstrate how this works with our hardware, we do this on 2 physical qubits. Again, it's a part of the 5-qubit device I've shown earlier. The idea here is that basically, once again, you can do the measurement of the ancilla after this gate. So if you start with a data qubit, for instance, in the X state, this is a tomography projected on the equator of the Bloch sphere. Then you can post-select on this result, and if the result is 0, you would have applied the T-gate, which is a pi/4 rotation as desired. And otherwise, if it's 1, you would have got the opposite, basically the opposite phase. So obviously, what you need to do here, if you want to do this deterministically again, is to correct this state using a pi/2 rotation to bring it back to the same phase. So this is what we did first. We basically conditionally on the result equal 1, we have our closed loop that will apply an S-gate. So in this case, you would obtain pretty much the desired angle with 92% fidelity all the time without doing the post-selection. Now, if you actually don't want to apply an S-gate, because an S-gate is also non-transversal, eventually, you will have to do a similar trick. So instead of doing the S-gate, you could replace this gate here with the equivalent, some very similar construction that instead of having the ancilla prepare in this state, would have the ancilla prepare in this other state. So the full circuit will become this nest loop, or let's say a full sequence that is conditioned on a measurement result. Obviously, in this case, the sequence becomes longer on average, which is why the fidelity is going to be lower than earlier. But again, this gate can be applied deterministically using this protocol, and it's an interesting case where we don't just apply a gate conditionally on the measurement, but a full sequence that can also include an additional gate or an additional measurement. So these were, again, all examples of 1 qubit and 1 measurement, pretty much, except in this case, the runtime of this sequence is non-predetermined. There are other cases we were explored, basically to test the hardware and try to basically implement additional functionalities. One of these is a so-called repeatancy success that has been proposed at Microsoft as a way to decrease the number of T-gates that will be needed to approximate an arbitrary single qubit gate. It's in this paper over here. So the idea is that you might want to repeat a certain number of gates until the condition is met. That's where the name comes from. So you will keep measuring some subset of this register, and once this reaches the target condition, then you will stop applying these gates, and otherwise you will keep going. So if these gates are successful, the measurement, the protocol stops, and otherwise the effective action will be identity, so one will just have to apply it again. Now, this protocol has also attracted recent interest for a possible implementation of a quantum neuron with superconducting qubits that relies indeed on applying some sort of repeatancy success to implement basically a nonlinear gate, a nonlinear operation on an input state, which is proposed here. So what we did in the lab was basically try to see if we can do it on a single qubit to start with. So we start with one of the simplest protocol that is in this paper over here. That is this, in order to implement this gate, that is some partial Z rotation. So this is the gate sequence. It's basically a bunch of single qubit gates with a couple of 2 qubit gates in between. And again, what we look for is the measurement result of the ancilla, so that if the result is 0, we have actually applied the intended gate. And if the result is 1, nothing ideally has happened, so one could just take this and repeat and try again. So that is the goal. So we basically try to do this. We start with an initial state, again, in a superposition. The first thing we do, we post-select on the result so we can see what's actually happening. So if we apply all these gates, we get, for result 0, we get the intended, basically the dashed line here is what we expect, and the solid line is data. We get this result with 87% probability, and if the result is 1, you see that the angle hasn't changed that much, but the coherence has shrunk significantly. That's just because you applied a series of gates anyway, even if the ideal result should be identity. So what the protocol says is now that we are at this point, you should repeat this again in this case. So that's what we do, or at least in this case, it's all done by post-selecting all these measurement results. If you do this again, you will get, again, the intended state with a reduced fidelity because it's, again, one more round. And in the other case, you see that you start to lose coherence almost completely. So we basically have a lower chance to guess the final state. So this is, again, probabilistic because you're post-selecting on every possible branch to see what's happening. Thank you. But we can also do this deterministically, which is by applying this feedback loop continuously in a way that it will keep basically repeating itself until the result is the one we want. As you can see, with the limited fidelities that we have for this device, 2 qubit gates and ancillary readout, we can't really gain much. But that's basically what happens when we increase the maximum repetition number from 0, which means apply only once, to basically as many as you can, letting it repeat. In the last 5 minutes, I want to give you a flavor of another type of experiment we've done recently that uses multiple measurements in order to basically do some operation. And the simplest case we implement is the majority vote, which there are 2 ways to do this. We started doing this in time, which doesn't make much sense by itself, but it was a way first to test the hardware, which is we don't have many qubits. We just repeatedly measure the same qubits. And the idea is that we basically want to determine as fast as possible if we get a larger number of 1 or zeros. But due to the short time, we skip the time majority vote and goes directly to the space majority vote over 3 qubits, which is actually what a majority vote should mean over multiple voters. So what we have here is basically 3 superconducting qubits in a similar device from the one I showed you earlier. And this is a readout matrix that correlate basically the prepared state to the assigned state. Ideally, what we would have here is a diagonal matrix showing that we can prepare state and read them out independently. And this is pretty close to what we expect. So there is a good sign, a good indication that we can perform the experiment. Another way to look at this is basically to look at the readout probability for each of these qubits in different states as a function of the other 2. And you can see there is very little dependence, showing that the readouts are pretty much independent from each other. So in order to do this experiment now, basically that's what we do. We prepare 8 computational states, and then we look at the probability that for this combination of states, the majority vote would be 0 or 1. What we see on the left is the voltage distributions for these 3 qubits, and we digitize each result in a calibrated way so that we can determine for each run of the experiment if we have measured a 0, 1. This is basically a histogram of different repetition of the experiments. And on the right, you see the majority vote probability equal 1. This is the first data point. As you can see, this is already data, but it's negligible that with the qubit prepared all of them in the ground state, the fast controller will basically be able to determine that the majority vote is 0, as obviously, but this is done in real time on the trigger distribution module. Then we can also change the initial state, for instance, to 0, 0, 1 by flipping one of the qubits. In this case, you start to see a little bit of error probability. And depending on which qubit you flip, the error might be lower or higher depending on the readout fidelity. But what I would like to point out here is that the probability is the same basically for both open loop and real-time results, meaning that we compare the post-process data that we just take the data and analyze them on the laptop later on, compared to the real-time experiment where the result of this majority vote, which is a simple function but could be any kind of processing of these measurements, that can be done right now in about 600 nanoseconds. And so on and so forth. What you see is that the majority vote will become 1 only when there are at least 2 excitations in the system. Obviously, this case will become, the majority vote will declare 1 with high probability. And as you increase the number of excitations, you see that it becomes even easier if you have all qubits in 1, because in this case, it would take 2 bit flips in order for this state to be determined for the wrong majority vote. So what this implies is that we can not only combine one measurement result with one action, but we can also now basically have the capability to process multiple measurement results that could be coming from different qubits or from the same qubit measured multiple times. And we can see that hardware results matches the post-process results, and the latency, I haven't shown you the majority vote in time, but they're basically the same. So I think I'm out of time, so I just want to conclude with summarize that we have demonstrated a protocol that starts to do some interesting difference between quantum and classical processing using a few qubits. There are other examples, one of which you will hear tomorrow. And the second, we are basically developing hardware that can hopefully be used for some implementations of machine learning, and I'll be happy to hear more about that. Thank you.
Questions?
So this is, of course, beautiful results in both cases, and I'm just curious, to what extent do you see the opportunity to tune your circuits using these techniques?
You're talking about the feedback control, I suppose. I think that's an interesting application for sure. It's not something I thought about, but I think the advantage there, I mean, in a way, the way we calibrate our circuits is some slow version of this. It's like you do some kind of slow loop where you literally transfer all the data to the computer, and then the computer, even if it's automated, is still done in the processor there, which takes time, obviously. And yeah, it would be definitely interesting in trying to do this faster, especially when the number of qubits grow, which means like you don't need to go back to the computer, but you can just do everything in hardware. That would definitely save time in the calibration procedure. But I don't know any actual concrete proposal on that, so other than the one you showed.
This is, of course, what is actually done in clocks.
Sorry?
In a clock, in an atomic clock.
Oh, I see.
Like in an ion clock in particular.
Okay. I see. That's interesting. Okay, thank you.
Questions?
So in the first part of your talk, you were showing the quantum advantage with respect to the classical protocols. How is the expectation when you increase the number of qubits? How will that advantage change? Or
yeah, the advantage, at least in theory, is expected to grow with the size of the oracle. And actually, this experiment here, it's done with 16 qubits, shows already that, to be honest, I don't remember the numbers here, but the gap is expected to increase with the size. Actually, I think I don't want to say something that I'm not sure about, but I believe that in theory it should be polynomially, for the classical case, should go polynomial with a number of qubits, whereas the quantum solver should do it logarithmically with the size. But take it with a grain of salt.
Okay, then let's thank Diego again.